Hey everyone, and welcome to this explainer on the chemistry of donuts. Today, we're not just looking at a baking recipe, we're actually embarking on a pretty fascinating scientific journey. I want to introduce you to our protagonist for today. Let's call him Doughy. Doughy is a tiny donut with a big dream of becoming the world's most delicious treat. But what Doughy doesn't know, and what we're about to uncover together, is the incredibly complex chemistry hiding inside every single bite of that journey.
Okay, let's dive right into this. What if your donut was actually a massive chemical reaction? I mean, it's so easy to look at a soft, fluffy donut and just see a simple, sweet treat, right? But from the moment flour first meets water, all the way to that perfect golden brown finish, there's a literal laboratory of chemistry working behind the scenes. We're going to reframe how you see dessert forever.
All right, let's start at the very beginning with phase one, the birth of Doughy.
So Doughy starts out as a collection of super simple, everyday ingredients: flour, water, or milk, sugar, eggs, butter, yeast, and salt. But hey, don't let their simplicity fool you. In the world of food science, these are Doughy's fundamental building blocks, and every single one has a highly specific job to perform. They aren't just sitting there in the bowl, they're actively waiting to interact.
Now, the very first major interaction happens when we mix that flour and water together. Flour contains two really specific proteins: gluten and gliadin. When they meet water and get mixed up, they physically link together to form gluten. You can think of gluten as a microscopic, elastic net. This net is absolutely crucial because it traps gases and gives the dough its stretchy, resilient texture. Without this elastic net forming right at the start, Doughy could never rise. He'd just be a dense, flat puddle. Actually, scratch that. He'd be more like a heavy hockey puck.
Which brings us to phase two, the great yeast awakening.
Okay, here's a pretty wild fact for you. Yeast is actually a living fungus. I know, it sounds kind of strange to think about a living fungus when we're talking about a sweet dessert, but this tiny organism is the true engine behind our hero's growth. Doughy is currently small and flat, but those tiny yeast cells are about to wake up and get to work.
So how exactly does this living fungus work its magic? Well, yeast absolutely loves sugar. It begins gorging on the glucose in the dough, and in return, it essentially burps out carbon dioxide gas, ethanol, and energy in a process called fermentation. Those tiny bubbles of carbon dioxide gas, they get trapped inside our elastic gluten net. As more and more gas forms, Doughy slowly grows larger and softer. It is literally exactly like blowing air into a balloon. And this brilliantly illustrates why temperature is just completely critical here. For Doughy to thrive, he needs a true Goldilocks zone. If the dough's too cold, the yeast just goes to sleep, and Doughy stays completely flat. If the dough gets too hot, the yeast actually dies, which is, a total disaster for our donut. But when you hit that perfect temperature state right in the middle, you achieve the ideal fermentation rate. The gluten stretches, millions of tiny air bubbles fill the dough, and Doughy becomes light and airy instead of heavy and dense.
Next up is phase three, surviving the hot oil.
180 degrees Celsius. That's about 350 degrees Fahrenheit. This is the exact temperature of the hot oil that Doughy jumps into. And let me tell you, at this extreme heat, a massive shock to the system occurs and multiple explosive chemical reactions begin simultaneously.
It is an absolute frenzy inside that fryer, as three distinct processes happen all at once. First, the water inside Doughy rapidly changes into steam, violently pushing outward to make him puff up even more. Second, the extreme heat causes the egg and gluten proteins to coagulate. They firm up, permanently locking Doughy into his final shape. And third, we have starch gelatinization. The starch granules absorb water and swell up, creating that perfectly soft, melt-in-your-mouth interior that we all love. And the craziest part, all of this action happens in just moments.
Moving right along to phase four, the golden makeover.
So the crucial point here is understanding exactly how Doughy gets his tan, which brings us to one of chemistry's most famous processes, the Maillard reaction. This is a chemical reaction specifically between sugars and amino acids. And I really want to emphasize this. Doughy's beautiful golden color isn't from burning. It's from this highly complex chemistry. The Maillard reaction produces hundreds of brand new flavor compounds, a deliciously rich aroma, and of course, that iconic brown crust.
And this specific reaction, it begins working its magic precisely within this thermal sweet spot, 140 to 165 degrees Celsius. Without hitting this exact window in the fryer, our hero Doughy would taste incredibly bland and look completely unexciting.
But the chemistry doesn't stop there. As the temperature of the crust rises even higher in the hot oil, some of the sugars begin to caramelize. Sugar molecules literally break apart and form entirely new compounds. Caramelization creates those deep, sweet caramel flavors, enhances the rich brown color, and gives off an intense, rich aroma. This beautiful combination of the Maillard reaction and caramelization is exactly why fried donuts smell completely irresistible.
Right after leaving the intense heat of the fryer, Doughy enters the cooling stage, essentially catching his breath. During this time, steam slowly escapes from the donut. This controlled release of steam is what allows the outside crust to become slightly crisp. Meanwhile, deep inside, the crumb stays perfectly soft because tiny pockets of moisture remain permanently trapped. He's cooling down, setting his texture and preparing for his decorations.
Now for the sweet makeover. And yeah, even these final touches involve food chemistry. Take a sugar glaze, for example, which is mostly just sugar dissolved in a little liquid. As it dries, the sugar crystallizes into a tight, shiny coating. Or if we use chocolate icing, the cocoa butter inside it is chemically structured to melt smoothly the precise moment it hits the warmth of your mouth. Even the sprinkles add a distinct color and crunch to the textural profile. Doughy is now a complete chemical masterpiece.
Now, what's really interesting about this slide is that it brings us to phase 5, the science of going stale.
Here is the scientific villain of our story: starch retrogradation. Because, sadly, Doughy's journey doesn't end at perfection. Every donut has a lifespan. After several hours sitting on a shelf, the starch molecules inside the donut actually begin to reorganize themselves. They crystallize and physically push out moisture. This retrogradation is exactly what causes Doughy to become firm, dry, and noticeably less fresh. It's the precise scientific reason why a fresh donut straight out of the fryer will always, always taste infinitely better than when eaten the next day.
Before we wrap up, I really want you to just think about the sheer scale of the science we just unpacked. One single donut contains millions of tiny air pockets. Every single one of those pockets is the result of a living fungus producing gas, proteins coagulating in extreme heat, and starches swelling to perfection. The scale of the chemistry happening inside just one donut is absolutely staggering.
Doughy's incredible journey proves that chemistry isn't just something found in sterile laboratories. It's happening every single time we bake, fry, or enjoy our favorite foods. You aren't just eating dessert, you're tasting gluten chemistry, fermentation, protein coagulation, and the famous Maillard reaction. So now that you know its chemical secrets, I leave you with this question: what food's chemistry will you discover next? Keep exploring and never stop looking for the hidden science in your everyday life.